All right, welcome back, and we are going to be proceeding into all of the rules for derivatives. So you can see this is our do now right now. I'm going to ask that you guys just do what's in the do now, and we're going to proceed from there. So you can see I want you to find f prime of f of x equals 6, f prime of f of x equals 3x, just using that limit definition from 2 sections ago, and then plug this into your calculator. If you're wondering what your calculator should look like, that's what your y2 should look like in your calculator. So pause, do that, and then we're going to come back. All right, cool. Let's get on the right screen. There we go. And differentiation rules. So you're going to have to use the limit definition of the derivative for the rest of your life. There are no shortcuts. Enjoy calculus. Ha 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 ha. Just kidding. You're going to learn a lot of rules today. There are so many rules that you're going to learn today. And you're probably going to want to write all of them down. And you're probably going to want to write them in a place where you can find them later. All right. So on your graphing calculator, enter any constant into y1. And the reason why we're entering any constant into y1 is because y2 has now become a differentiator for this calculator. So I don't know, some constant you like is possibly like 1, looking at that. If I was to graph this, I can now see there's the graph of y equals 1. There's the graph of the derivative of y equals 1. And this is going to work for any constant, 5. I'm going to get the same graph of the derivative. And when we look at the graph of the graph of that derivative is just y equals 0. Why does this happen? Because the slope of any function, or any constant function, is 0. Therefore, your first rule that you are going to learn this section is the derivative of any constant is 0. So we do have a couple of examples here. If y equals 3, then y prime is equal to 0. Let's just throw this down here, something that really screws with people. D dx of pi, and you don't know why this is going to screw with people yet, but the derivative of pi cubed is just 0. Any constant, the derivative of any constant, e, is equal to 0. All right? So that's your first rule that you have to know. Write it down, memorize it. So type x squared into your into y1. Type x cubed into y1. Type x to the 4th into y1. Type x to the 5th into y1. Because you know what each of these functions look like, if you take the derivative of x squared, you are going to get a linear function. If you take the derivative of x cubed, you're going to get a quadratic function. If you take the derivative of x to the 4th, you're going to get a cubic function. Just to ruin the big surprise for you, when you take the derivative of a power, it reduces the power by 1. But a little bit further, it also takes the exponent and makes it the coefficient of the derivative. So looking here, here's a nice little example. If f of x equals x to the 4th, then f prime of x is going to equal 4x cubed. We've taken the exponent, moved it in front, and subtracted 1 from the exponent. Or x to the 8th is our function. The derivative of x to the 8th would be 8x to the 7th. Let's say I'm finding the derivative, and keep in mind when I say d dx and then something, that's just saying take the derivative of. So it's a little bit shorter away than this. The derivative of x to the 32nd is 32x to the 31st. Take your exponent, drop it down, and then subtract 1 from your exponent to get your new function. Now looking down here, this may look a little bit harder to deal with, that 1 over x, unless you remember 1 over x means x to the negative 1st. So if f of x is equal to 1 over x, f prime of x is equal to negative 1 times x to the negative 2nd. Take your exponent, drop it down. Take your exponent, subtract 1. If I look at this, square root of x. You learned in Algebra 2, square root of x is equal to x to the 1/2 power. So if f of x is equal to the square root of x, f prime of x is going to be equal to 1/2, take your exponent, bring it down, x to the, and then we have to do 1/2 minus 1. 1/2 minus 1 gives us negative 1/2. So the derivative of the square root of x is 1/2 x to the negative 1/2 power. I like to write that, since I've got the negative exponent, it brings it to the bottom and makes the derivative of square root of x 1 over 2 times the square root of x. And that derivative pops up a lot. So I just I have this one memorized as like an extra kind of rule. Anytime I've taken the derivative of the square root of x, I just know it's 1 over 2 square root of x. But you use the power rule for any other index. Like if I'm trying to find the derivative, let's just throw out another example, the derivative of the cube root of x. That's a little bit more difficult to figure out. You would rewrite that as the derivative of x to the 1/3 power. So this would become 1/3. X to the 1/3 minus 1 gives me negative 2/3 power. So again, a bunch of examples to get you the feeling of how this is called the power rule, how this works. So now you have two rules that you have to memorize. The derivative of any constant is 0. The derivative of any x to a power is going to be n x to the n minus 1. So 2 rules down, I think like 10,000 to go. So now that we know that the derivative of x squared is 2x, what happens if we multiply it by a constant? So you could actually graph the derivative of 0.5 x squared, of 2x squared, of 4x squared. I'm just going to ruin the surprise for you guys. When you take the derivative with a constant, the constant stays there. So there's the rule. The derivative of c times, we'll call it u, is c times the derivative of u. So if I'm talking about putting it in terms of the power rule, the derivative of c, where c is any number, x to the n is c times n x to the n minus 1. And this part right here is just the power rule with the constant in front of it. The derivative of 7x to the 5th is 7 times 5, x to the 4th. The derivative of 4x to the 12th, derivative of 4x to the 12th, is going to be 12 times 4x cubed, or just 48x cubed. And I know some of you are big into like showing as little work as possible. This is an easy problem. If I was doing this problem, I would go from 4x to the 12th to 48x cubed. You do not have to show me that you're doing 12 times 4. I trust that you know how to do 12 times 4. What if we add functions together? I'm again going to ruin the surprise. We happen to know that the derivative of x squared is just 2x. Ooh, this one's a little bit more difficult. That guy right there, the derivative of x. Surely we didn't talk about the derivative of any linear function. The derivative of x, you can look at it in 2 different ways. X is just a linear function. You can find the slope of that linear function. You could also look at this as x to the 1st, and then we would have 1 x to the 0th power if you really want to use the power rule for it. So this would be just 1. But I mean, this works for any linear function. The derivative of 7x, since we just used the constant rule, we can, or the constant multiple rule, we can find out, since the derivative of x is 1, the derivative of 7x would be 7 times 1, or just 7. Really, when I look at this, I just see that this is a linear function. Linear function has a constant slope. The slope is the same at all points. It's just 7 there. But back to why I'm doing that. Taking the derivative of x squared plus x, well, I know the derivative of x squared is 2x. I know that the derivative of x is 1 from what I just did here. So if I take the derivative of x squared, not x squared squared, that's my bad, plus x, the graph of that is going to be that 2x plus 1. Basically what we're looking at here is what's called the sum and difference rule. The sum and difference rule says just take the derivative term by term. So if you're talking about the derivative of u plus v, that would just be the derivative of u plus the derivative of v. Same thing with subtracting. Derivative of u minus v is derivative of u minus the derivative of v. And here's several examples that you have, or a couple of examples, I guess. I shouldn't say several. My wife gets mad at me when I use the wrong term there. Y equals x to the fourth plus 12x. Take the derivative of x to the fourth, 4x cubed. Take the derivative of x to the fourth, 4x cubed. Take the derivative of 12x. Well, that's just a linear, so the derivative is just its slope, 12. Taking the derivative of x to the fourth minus 2x squared plus 2, you just have 4x cubed minus 4x. Derivative of x to the fourth, derivative of 2x squared. Oh, but wait, what happened to this 2? It's plus 0. And nobody in their right mind actually puts down plus 0. So just to throw up another example, the derivative of x to the 32nd minus 4x to the 11th plus 7x cubed minus 12x plus 14. It looks like a really long, complicated problem to do, and if I was to use the limit definition of this problem, this would take me for frickin' ever, because I would have to do that x plus h to the 32nd. But since I now know all my shortcuts, I can just do term by term. 32, x to the 32 minus 1, 31st, minus 4 times 11, 44, x to the 10th, plus 7 times 3, 21, x squared, minus derivative of 12x, 12, plus that differentiate. We like to use the phrase differentiates out. So 14 differentiates out. It goes bye-bye. When you take the derivative of a constant, it becomes 0, and it is no longer there. All right? So now we've had a lot of rules there. Whew, man, so many rules. Now we want to apply those rules to a couple of different types of problems. Like one is being able to find the horizontal tangent of a function. To find the horizontal tangent, we need to first find out what is the equation for all the tangent slopes. And then we need to find out when we have a horizontal tangent, that just means the slope is equal to 0. So we're going to find the equation for the tangent slopes. We're going to take that equation, set it equal to 0. So looking at this, I've got y equals x to the fourth minus 2x squared plus 2. That means my y prime is going to be equal to derivative of x to the fourth, 4x cubed minus 2 times 2, 4x, period. 2 differentiates out, the 2 minus 1 becomes 1. All right? Set equal to 0. Again, we set it equal to 0 because it says what are the horizontal tangents. Horizontal tangent means slope equals 0. So now I just need to be able to solve this algebra 2 equation. And you have to find out some way, shape, or form to find this equation. I happen to see that I can factor out of 4x. I got 4x times the quantity of x squared minus 1 is equal to 0. And now I know the 0 product, well actually, I could even factor that further, but no, I don't want to. I know the 0 product property says either 4x equals 0 or x squared minus 1 equals 0. Going a little bit further, I need to solve this. I got x equals 0 or x squared equals 1 or x equals plus or minus 1. So I've got 3, I want to emphasize what I'm about to say here. I've got 3 locations of my horizontal tangents, but I don't have 3 horizontal tangents. To find out what the horizontal tangents are, horizontal tangents refer to the actual line. So I have to write the equation of the line. Well, I happen to know that the equation of a horizontal line is just in the form y equals a number, and it's whatever height that function has to be at. So in order to find out what these horizontal tangents are, I need to take my x value and plug it into the original function. So essentially what I'm doing is I'm doing y when x equals 0. I'm introducing a new symbol. I think I've used it a couple times with you guys before, but when I put this bar with a number at the bottom here, it means evaluate this function for this value. So I'm going to have 0 to the 4th minus 2x squared plus 2 times 0. Got to remember plugging it in everywhere. Plus 2. 0 to the 4th minus 0 plus 2 gives me 2. One of my horizontal tangents is y equals 2. There's one of my horizontal tangents. Evaluate y when x equals -1. We've got -1 to the 4th minus 2 times -1 squared plus 2. Whew, almost messed that up. So this is +1. This is +1. So I've got 1 minus 2. 1 minus 2 is -1 plus 2 gives me 1. So another horizontal tangent that I have is y equals 1. And then the final horizontal tangent that I have is at x equals 1. Some of you, I'm sure, are recognizing that because the original function was even, notice all the even exponents, that means f of -1 is going to equal f of 1, aka 1 minus 2 plus 2 is going to give me 1. So I really only have 2 horizontal tangents. And how does that work? Why is it that I have 3 locations for the horizontal tangents, but 2 horizontal tangents? And just because I don't feel like typing it out right now, I already have it produced for you. You can actually see, I kind of have a W shape right here. And 2 of those horizontal tangents are coincident with each other. And then the third horizontal tangent is right up there. All right. So again, what I wanted to emphasize there was the difference between what the horizontal tangent is and what the location of the horizontal tangent is. The location of the horizontal tangent is at x equals 0 or plus or minus 1. The actual horizontal tangents are y equals 2 and y equals 1. So how I would phrase that is the function has horizontal tangents at -1, 0, and 1. Those horizontal tangents are y equals 2 and y equals 1. So again, some tricky vocab that we really have to emphasize here. Oh my frickin' goodness. This one, it's not that bad. You want to write it down, and you definitely want to write down the example for this one. So we have the derivative of u times v is u times the derivative of v plus v times the derivative of u. Notice that this is not just the product of the 2 derivatives. That is the #1 mistake that I see when people try to find the derivative of a product of 2 functions. So again, u times the derivative of v plus v times the derivative of u. Since we have addition right in here, we know that addition is commutative. The way that I memorize the product rule is the non-derivative of one times the derivative of the other plus the flippity-floppity. Someone a few years ago memorized this as you have the derivative of a left and a right. You can make it left d right plus right d left. Any way that you can do this to memorize that you're not just doing the derivative of each and multiplying them together. There's a little bit extra to it. So let me just show you what I mean here. So there's actually 2 different ways to do this problem. One of these ways is to actually do the FOIL and take the derivative. The other way is to use the product rule. Let's do the product rule first because that's the way that we're learning right now. Now keep in mind in math, if you do one thing 2 different ways, you should still get the same correct answer. I'm going to move this over just because I know I'm going to need a crap ton more space. I think you guys can still see that. Yeah, you should be able to still see it on your screen. Of course, now the white box is a little bit screwed up here. There we go. So now in order to do the left d right plus right d left, what we are going to change this into, we keep the first function the same, this guy right here. That's left times d right. D right is the derivative of 2x squared, so, 2x cubed, so 6x squared plus 5. That's half of our derivative. We have left d right plus right 2x cubed plus 5x d left. D left here would be the derivative of x squared plus 3. So just times 2x. That is an acceptable answer. Of course, some of us don't like seeing all of this, non-simplified crap up here. So some of us might have to actually do the foiling. So we'd have first 6x to the fourth outside plus 5x squared inside plus 18x squared plus last 15 plus distribute your 2x, so we'd have 4x to the fourth plus 10x squared. And then of course if we go that far we might as well combine like terms. So let's see, the biggest term that I have here is the fourth power, which has 6x fourth and 4x fourth, so 10x to the fourth. Second power, so 5 and 18, 23, 33, so plus 33x squared plus 15, right? So any of these three answers is going to be acceptable for me. Any of those three answers, whether you leave it unexpanded, all the way expanded, or if you simplify it as much as possible. Now I did say that there are two ways to do this problem. I know in the bookwork there's at least one problem that says verify that you get the same answer for these. So the other way that I could do this, instead of trying to do the product rule, I could do the foiling first. So foiling, I would have 2x to the fifth, x squared times x third, yeah. 2x to the fifth. Plus, outside, x squared times 5x would be 5x to the cubed. Inside, 3 times 2x would be plus 6x cubed. Last would be plus 15x. And once I expand that, notice I haven't taken the derivative, so this would not be an acceptable answer, but the derivative of it would be. And I know some of you might be pointing out that we got common like terms there. So 2x fifth plus 11x cubed plus 15x. And we should be able to see, as long as we do the power rule appropriately, we should get the same answer. And some of you are probably marking it down in your notes. Yeah, it's the same answer. 2 times 5, 10, x to the 5 minus 1, fourth, plus 11 times 3, 33, x to the squared, plus 15. So long story short, which way do you have to do it? Either one. Whichever one you find easier, whether you FOIL it out and then take the derivative, or if you, FOIL it out, then take the derivative, or product rule and then FOIL, or heck, just product rule and don't worry about the arithmetic there. Any one is possible. Now, one caution that I would give each and every one of you, if you are trying to always do the expanding, keep in mind when we get to some other trickier functions, you're not really going to be able to do that, so you do really want to practice with the product rule while it's still a little bit easier. Just to give you a feel for what I'm talking about, eventually we're going to be taking like the derivative of x times sine of x, and there's no way to FOIL those out, so you would be kind of SOL, which stands for sorta out of luck when it comes to those problems. So there's the product rule, and I know some of you probably envisioned that the quotient rule was going to come next. Unfortunately, with the quotient rule, order does matter. So we know that quotients, division, is not commutative, unlike multiplication. We know that subtraction which comes up in the quotient rule, is not commutative. So it is very important to make sure that you get this in the right order. Now, I have a mnemonic to remember which one comes first. It's basically like 1 times the derivative of the other minus the other way around over the 1 squared. So what I look at here is I look at this as the derivative of the high over the low. Okay, so this is not official math terms, but the high is the higher up one, the low is the lower down one. Right? So the rhyme or sing-songy thing that I remember for this one is, it is low d high minus high d low over low low. Low d high, high d low, low low. All right? That's the way that I have it memorized. It works for me. Honestly, if I'm telling you 100% what I did when I was in high school and I learned the quotient rule, I did not know low d high, high d low, low low. Somebody told me that when I got to college or maybe even after college. Every time that I took a test on derivatives, I had to look at the quotient rule right before I took the test, just so that I knew which one was non-differentiated at first. I'm going to give you an example of how this works. Unfortunately, you really can't do the foiling on this because we have division. Division, FOIL doesn't apply to division. But looking at this, I know that I'm going to have a huge, humongous fraction. Again, low to high, high to low. Low, what's the low? The low is the bottom one. X squared plus 3. So I've got x squared plus 3 times the d high. So the d high just means derivative of the top. Derivative of the top, I've got derivative of 2x squared is 2 times 3 is 6. 3 minus 1 is 2. So I've got 6x squared. Plus derivative of 5x, 5. Minus. So I got low d high, now it's high d low. High means don't do anything to it. D low means take the d of it. And d means derivative. Derivative of the low is derivative of x squared is 2x. Derivative of 3 is nothing. Low low just means x squared plus 3 squared. Am I all right leaving it here? Abso-frickin-lutely. That is fine to leave it here. Now, just because I don't like it like that, because I am a math teacher, I personally would expand it. So I would have the FOIL, so 6x squared times x squared gives me 6x fourth outside plus 5x. It's 5x inside plus 18. Oh, 5x squared. Ooh. 18x squared plus 15 minus, now here, keep in mind we have to distribute the minus and the 2x, so it would be minus 4x to the fourth. I realized that weird noise made no sense for you guys, but I had to lean over backwards so that I wasn't blocking my projector so I could see it. Plus 10x squared. All over, and I'm just going to give you guys a nice clue for later in this course. Never expand the denominator. Just always leave the denominator as whatever the original denominator was squared. And now since I came this far, I might as well finish it up. I got 2x to the fourth, 23. Oh, wait, I forgot to distribute my minus there. Yikesies. That should be minus 10x squared, so 23 minus 10 gives me plus 13x squared, and then plus 15 all over x squared plus 3 squared. Whew! A little bit of arithmetic exercise there, isn't it? It can get a little bit tedious when you're doing problems like this. Now, because we like to make sure that we are right on these problems, you might want to use your graphing calculator just to check it. Now, what's really cool here is we already have our checker set up in this in our calculator. Having this allows us to, in the first line, put the original function. So the original function was 2x cubed plus 5x over x squared plus 3. 2x cubed plus 5x over x squared plus 3. X squared plus 3. What I'm going to do is I'm going to turn off the original function. And in the third line, I'm going to put my answer. And as long as my answer is correct, these should be the same graph. X squared plus 3. Squared. All right. Fingers crossed that they come out to be the same thing. Okay, that's going kind of slow. Whatevs. Okay. Not really an interesting looking graph. But I can see as they graph, they end up being coincident with each other at all points. And therefore, what I wanted, which was the derivative of that first function, is equal to what I wrote over here. Because again, I can look into my grapher right here. I'm using this as a checker for myself. All right? So, let's see here. I think we have all of the rules for today, at least. There's many other rules, so many other rules that we have to conquer. But that's the rest of this chapter. Before we get there, we do want to talk about doing things symbolically. So looking at these three expressions right here, you have to know that u of 1 is equal to -4. You have to know that u prime of 1 is equal to 1. V of 1 is equal to 3. V prime of 1 is equal to -2. This question should actually say, find all of these for x equals 1. You can't find this anywhere other than x equals 1. And what you're trying to do here is you're really just trying to apply all those rules. So I can see uv, that just means a product of two functions. So this is going to be u times v prime plus v times u prime, which in this case I now have actual numbers. So u is -4 times v prime would be -2 plus v, which is 3, times u prime, which is 1. And then, of course, just 8 plus 3, get 11 off of that. Again, doing this symbolically, low to high, high to low. So low d high minus low d high minus high d low over low squared. You might run into some difficulty if your v's and your u's look exactly the same. Start putting tails on your u's. So now here we're going to have v was 3, u prime was 1, 3 times 1, minus u was -4, v prime was -2 over v squared, so over 3 squared. I'm just doing the math. 3 minus 8, so -3 minus 8, -5 ninths for that one. And what I consider to be the easiest one, u prime plus 3 v prime, is just going to be u prime was 1 plus 3 times v prime, -2. 1 minus 6 gives me -5. -5. Right. Ooh, find the equation of the tangent of the line tangent to the function below at the given point. Yikes, this scares me. So multiple ways that we can do this. One, I see that, I imagine that some of you recognize that we have a quotient here. Anytime you have fractions, you should really be thinking about the quotient rule. So that low, the high, minus high, the low, over low squared. So looking at that, you would have the low x times the d high would be 2x, so x times 2x minus x squared plus 1 times 1 all over x squared. However, there is an easier way to do this, and I'm just going to bring that up real quick. If we didn't want to use the quotient rule, since my sum is in the numerator, I can rewrite y as x squared over x plus 1 over x, which would just be x plus x to the negative first. The reason why I bring this up is because in order to find the equation of the line tangent to the function, I need to find y prime. Again, you could do that low to high, high to low. Either way, you're going to get the same answer, or I can find the derivative of x plus x to the negative first. Derivative of x is 1. Derivative of x to the negative first plus, bring your exponent down, negative 1. X to the negative 1 minus 1 gives me negative 2. To find the slope of the tangent line, all I need to do now that I know the equation for the derivative, all I have to do is plug in the value that I want to plug in there. So I've got my slope, I guess I should say. Slope is equal to y prime at x equals 2. Y prime is equal to 1 plus negative x to the negative second. So this is going to be equal to 1. I guess I can change the plus negative to minus 2 to the negative second. And really the only difficult part here is going to be finding out what 2 to the negative second is. I know that that's going to be 1 minus negative, means put it at the bottom of the fraction. 2 squared gives me 1/4. 1 minus 1/4, my slope is 3/4. And if you really wanted to do it using the quotient rule, you could have done it using the quotient rule. All right. Next thing we have to do, I've got my slope, I've got my x1, I really only have to find my y1. So my y value is going to be equal to 2 squared plus 1 over 2, which is going to be equal to 5 halves. To find the equation of the tangent line at the given point, I just have y equals my slope, 3/4, times quantity of x minus x1. x1 was 2 plus y1, which was 5 halves. That right there is the equation of the line tangent to the original curve at x equals 2. So just to be clear on this, I can go back in here and I can again use my calculator to check myself, lest I wreck myself. Okay, alpha y equals fraction, what was it again? X squared plus 1 over x. X squared plus 1 over x. And the equation of my tangent line, what I think is 3/4 times the quantity of x minus 2. I said 3/4 times the quantity of x minus 2 plus 5 halves. And if all goes right, oopsies. If all goes right, it should look like a tangent line. And there's my rational function. And there's my tangent line right there. Again, just graphing them to make sure that I did it right. I think there's really only one more concept today. And that concept is the concept of a higher order derivative. A higher order derivative just means take a derivative. That's your first derivative. Bear with me. You take the derivative of a first derivative, you get a second derivative. If you take the derivative of a second derivative, you get a third derivative. If you take the derivative of a third derivative, you get a fourth derivative. So you can keep going on like that. Like once you get to the 31st derivative, you take that derivative, you will get the 32nd derivative. You have to have notation down. Using the prime notation, for each derivative, you just add another apostrophe. All right? So y double prime, y triple prime, y quadruple prime. At some point, we stop writing the tick marks just because it's hard to figure out how many you have written there. So at some point, we just go to the Arabic numerals right up here, just put them in parentheses. So y with an exponent in parentheses of 4 means fourth derivative. That's not the way that I like to write out higher order derivatives. I like to write them out like this. d2y dx2. The third derivative would be written as d cubed y over dx cubed. You don't really read them as d cubed y over dx cubed. I just do that so that I can write it so I can read it as I'm writing it. Really, it would just be read as the third derivative of y with respect to x. And the fourth derivative would be d4y over dx4. So basically, when you're in Leibniz notation, it's whatever the exponent is in the Leibniz notation, that is the order of your derivative. Again, my preference personally is the Leibniz notation. It just looks cooler than all these tick marks. Yeah, but it's all subjectivity at that point. Probably with y'all being like neophytes at calculus, you're probably going to side more with the tick mark notation, the prime notation, but you're wrong. So whatever. Let's calculate a fourth order derivative. All right. So calculating a fourth order derivative is not going to be hard. And now I just denigrated the prime notation, so I better use the correct notation here. So dy dx is going to be equal to 8x plus 2. All right? Now we have the first derivative. We want to get all the way to the fourth derivative. To get to the fourth derivative, well, we better go through the first derivative, second derivative, third derivative. d2y dx2 is going to be equal to derivative of this, 8. 2 differentiates out. Awesome. Third derivative of y with respect to x is going to be equal to the derivative of 8. 0. Fourth derivative of y with respect to x is going to be the derivative of 0, since 0 is a constant. 0 is the first example of a function that is its own derivative. I know of exactly 2 functions that are their own derivative. One is y equals 0. The other is, I'm not going to tell you until later. It comes up in this chapter. By the end of this chapter, you will know how to calculate every single derivative of every single function in the world, except for hyperbolic functions. There's a suggested assignment if you want to do it, but tomorrow in class, we're going to be doing massive, massive practice. So many rules, you have to know all of the rules, and this was fun. Let's do this again sometime.